While we're getting the presentation set up, it's my pleasure to welcome everybody to the Micron School of Materials Science and Engineering weekly seminar. My name is Eric Jankowski. I'm the director of the Micron School of Materials Science and Engineering. This is our weekly time to come together as a community across various interdisciplinary research projects. And it's my pleasure that this week we have student presentations from students from Kyushu University. This is part of the Upwards grant that Karthik will explain a little bit more as I pass the mic to him. But this is a reminder that each week we've got folks from the community, from other universities that come together in this room. And I encourage you, if you see a new face in the conversations afterwards or in the Q&A, go talk to somebody new that you don't know in this room and help broaden our networks to learn new things about materials together. So welcome everybody. Dozo yoroshiku. I'm going to pass the mic to Karthik to introduce our speakers for this week.
Thank you, Eric. Hi, everyone. For those of you who don't know me, I'm Karthik Srinivasan. I'm an assistant professor in the Electrical and Computer Engineering department. And it's my pleasure to introduce a variety of students that are here from Kyushu University today. So as Eric mentioned, this is part of the Upwards program, which is a collaboration between academic institutions in the US and in Japan with partnerships from Micron and Tokyo Electron. And the goal of this grant and this program is to foster exchange of ideas, exchange of students, and exchange of research that allows us to make advancements in semiconductors. So as part of that, we are hosting 10 students and 2 professors from Kyushu University, and we'll be having 5 of their students present today in MSc seminar, and 5 other students will be presenting in the ECE seminar next week on Wednesday at 10:30 a.m. downstairs in MCMR 106. Just a bit of an advertisement for that. So with that, I will go ahead and introduce our first speaker for today. Our first speaker is Satoshi Kumamoto, and you see his title there, but I'll let him do the rest of the introduction, and I hope you all find this quite enjoyable.
Thank you. I'm Satoshi Kumamoto. I'm undergraduating Kyushu University, Japan. Today, I'd like to talk about a promising material for optoelectronic devices. Excuse me. Oh, thank you. I'd like to introduce Zion acido-binary alloys of zinc oxide and indium nitride. Zion has a tunable band gap, a high carrier mobility, a high optical absorption coefficient, and a moderately high exciton binding energy. Because of these excellent properties, Zion is promising material for excitronic transistors, which are next generation semiconductors. Zion is also expected to be a photocatalytic material. In a previous research, the valence band maximum and the conduction band minimum of a Zion film on a cost-effective substrate were shown to be highly consistent with the redox potential of water and hydrogen production by water splitting, and the simulated solar lamp irradiation was confirmed. However, lattice mismatch substrate with cost-effective are not available in Zion. Sapphire substrates are very superior in terms of quality, productivity, and cost, but the low crystal quality is caused by a lattice mismatch rate of over 20%. Another problem is a limitation of gross temperature due to the thermal instability of indium nitride bonds. These images shows XRC of indium poor Zion film and indium rich Zion film deposited at 300 degrees Celsius. Indium nitride bond decomposes at temperature above 550 degrees. To achieve high crystal quality at temperatures below 550 degrees, it is necessary to ensure atom migration on the substrate surface by means other than increasing the substrate temperature as the long migration lengths of atoms during film growth is crucial for them to reach their thermodynamically favorable positions. In this study, we are aimed to realize high-quality enzyme-rich ion films on general-purpose substrate under the constraints of large lattice mismatch and low substrate temperature by controlling the surface morphology of the buffer layer. To solve these problems, we adapt 3D buffer layer using the inverted escape mode. In this study, in the inverted escape mode, the addition of nitrogen in the initial stage of growth lowers the surface energy and grows high density microcrystalline grains to relax the strain at the grain boundaries. Subsequently, grains fuse on this three-dimensional island layer and grow in 2 dimensions, resulting in single crystal growth on a lattice mismatch substrate. Next, I will introduce the experimental method. All films were fabricated by RF magnetron sputtering. The composition of indium is 50%. This is an AFM image of the buffer layer. In this study, the surface morphology of the buffer layer was controlled by controlling the thickness of the buffer layer. The Zion films were then fabricated on each buffer layer, and the relationship between the crystal quality of Zion film and the surface morphology of the buffer layer was investigated. The figure on the left shows X-ray locking curve of Zion films deposited on the sapphire substrates and the buffer layers. In the previous figure, it can be seen that the use of the buffer layer produces a higher quality enzyme-rich Zion film than a Zion film deposited directly on a sapphire substrate. In addition, as can be seen from the phi scan on the right peak, due to six-fold symmetry can be observed. The highest quality enzyme-rich Zion film is obtained on the buffer layer with a thickness of 1.6 nanometer, indicating that the crystal quality of the Zion film is strongly dependent on the thickness of the buffer layer. So for quantitative analysis, we define the figure of merit of Zion films as the rate of the integrated sharp peak intensity to the integrated broad peak intensity of the XRC, plotting it against the inverse of the RMF's roughness of the buffer layer. The correlation coefficient is 0.99, which is very high, indicating that the small roughness of the buffer layer is important to obtain a high quality enzyme-rich Zion films. Next, we show the surface height distribution obtained from the AFM image of the buffer layer. As shown in the left figure, the negative and positive parts of the height distribution correspond to pits and spikes on substrate surface, buffer layer surface, respectively, which are thought to inhibit the migration of atoms. Therefore, the quality of the Zion films on the buffer layer with thickness of 4.8 and 11.5 nanometer is considered to be degraded due to the spreading of this surface height distribution. It can be said that it is necessary to maintain low roughness during the deposition of the buffer layer on sapphire substrate and to form 3D islands while suppressing pits and spike components. This is conclusions and future plans. Thank you so much for your kind attention.
All right, we have time for 2 questions. Yes, Elton.
Hi, in your process for depositing the zinc oxide, how were you controlling the concentration of nitrogen in the film? Was that your contaminant? And then two, what was the temperature for the deposition process?
Temperature? So I'm so sorry.
I think your buffer layer is zinc oxide
Yes.
with some small amount of nitrogen.
Yes.
What was the temperature?
We fabricate the buffer at 780 degrees Celsius.
And how do you control the nitrogen? Is it just a flow ratio?
When fabricating buffer, the we add nitrogen about 24 SCCM.
Thank you.
All right. So I think because we have 4 other presentations, I would like to move on to the next speaker. Let's give another round of applause. All righty. Our next speaker is Kazuki Nagamine, and he will be presenting our second presentation for today.
Okay. Hello everyone. My name is Kazuki Nagamine from Kyushu University. And my mentor is Kamataki Sensei. It's right here. So I'm talking about the impact of helium addition and the addition and on the hydrogenated amorphous carbon film that deposited by the acetylene based PCVD. So that before I'm talking about my topics, I'm talking about the Kyushu University. So the Kyushu University is the western, is this area of the western Japan. So this area. So the Kyushu University is located here and North Kyushu Island. And the Kyushu is there, and many companies fab semiconductor fab there is in Kyushu. So Kyushu University is studies many many study about semiconductors. So I'm talking about my topic. So in semiconductor fabricating there, and so this is many process there. There's many process for semiconductor fabricating. So lithography and etching, then ion doping, then the deposition. So that I'm talking about the deposition. So deposition, in deposition, the many methods is used for the fabricating, but I'm talking about the PCVD and plasma enhanced chemical vapor deposition. It's a deposition. So this method uses the plasma. So plasma. So the next slide. The problem there. So there is a problem and from the miniaturization and the high aspect ratio. So the semiconductor device size is smaller and smaller by year, and higher aspect rate and higher aspect ratio. So there it is in the problem, so that thickness of photomask is decreasing. So the problem, the decrease the etching resistance of the photomask. And the previous research there suggests that the solution, so the use with the hard mask. What is the hard mask? The hard mask has higher etching resistance than the photomask, and hard mask is used after the being transferred from photomask. So this figure. And the hard mask is made of the material like the silicon nitride and silicon dioxide and and amorphous hydrated amorphous silicon. So my research is this material, hydrated and amorphous silicon. So the property is more hydrated amorphous silicon. So the higher etching resistance than the silicon nitride and the silicon dioxide, and the lower fluorescency as more suited for pattern dimension scaling. So the device so the transistor size is smaller. It's smaller by the year. So it is the so it is suitable for the pattern dimension scaling. So the ACH ACH film that is used in the EUV lithography, but the two challenges ACH film have. So the one problem is the thick ACH film have a high film storage, so they're causing the film to peel off and break down. And one more problem is low density ACH film have a low etching resistance. So the company so the reduction reduction of stress and the increase in the mass density are required. And however, so the film stress and mass density have a proportional relationship. So the mass density is when mass density is increased, so the stress is also increased. So my focus is developing ACH film with low stress and high mass density in PCVD. Okay, so my detailed experiment. So my objective is the investigation of impact of the helium addition. So on the helium addition on the film property of ACH film fabricated by the made by the acetylene and argon PCVD, plasma PCVD. So that this is the experiment machine. So this is the capable coupled plasma reactor, and this is experiment setup. So our group changed this helium contents. So the total gas flow of the argon and the helium is fixed, but the helium content is very varied, and this is result. So the argon helix mix ratio, so this increases. So the film storage is decreased from the 4.8 gigapascal to the 3.0 gigapascal. And the deposition rate is changes by the it's not on note. So the standard 3.0 gigapascal and the deposition rate is changes, and while the mass density remain constant. This result this result possibility of the contouring the film the storage by the changing the mixing ratio. So the changes the stress. So the cause of the changes stress. So it's considered to be the helium ion and the helium metastable. So the previous research so the Shiran and the helium PCVD, the report is that this association is promoted by the helium ion and the helium metastable. Okay, that's all. Thank you very much for kind attention.
All right, we have time for one question.
Thank you. Excellent. Can you comment on the difference between using acetylene and maybe like methane, CH4?
So the next experiment I'll conduct experiment on the methane, the helium. So in my opinion, so there, yeah, it's same. So it's same result. It's same result. So I will show that the same results.
Thank you.
All right, let's give our speaker another round of applause. All right, our next speaker is Ito Masaki. And Ito, the floor is yours.
Hello everyone, I'm Ito Masaki and I am Kyushu University student too. I'm talking about study of gas flow visualization using LSPR gas sensor. Here is content. I will explain the principle of LSPR where metallic nanoparticle is irradiated by incident light. Polarization P is induced. The P is expressed by the following equation. Okay. The P is expressed by the following equation, and the dielectric constant of metallic nanoparticle has an imaginary part, and P does not become zero, but takes a very high value. The resonance condition in this case can be expressed in terms of the dielectric constant of the surrounding medium. In other words, the absorption peak wavelength of metallic nanoparticle depends on the dielectric constant of the surrounding medium. As shown in the right figure, when incident light is irradiated onto the SPR substrate, which is an aggregate of metallic nanoparticles, the peak wavelengths of absorbed light are different for light passing through air and light passing through gas. As a result, the gas can be detected as a change in optical properties. This is LSPR substrate. Color changes in area expose the ethanol gases. Advantages are reversible response and fast response and recovery, and high spatial resolution. But the sensor does not have molecular selection system, basically. The LSPR sensor has potential to detect even very slow changes in gas flow. The objective of this study is development of a gas sensor that visualizes a weak gas plume. This is a gas sensor I made for this experiment. I'll explain the procedure of the experiment. First, we fill the gas source with gas and start photographing gas being volatilized. Next, we visualize gas flow based on the amount of change in transmitted light. Fabrication process of LSPR substrate. The LSPR substrates used in the experiment were prepared by sputtering gold nanoparticles and silver nanoparticles onto a glass. Next, annealing at 200 Celsius for 1 hour to agglomerate the particles on the substrate surface and make the deposition state uniform. We conducted 2 experiments. In the first experiment, we placed granular solution in the gas source and recorded the volatilization process for 11 minutes. In the second experiment, we recorded the volatilization process in the same way as in experiment 1. However, after 5 minutes and 30 seconds, we applied a weak airflow from the side. This is images video taken in experiment 1. The change in luminous intensity is so small that the gas flow cannot be visualized with the captured images as they are. So analysis is needed. The average of each of the 5 images was taken and compressed into a single image. Noise was removed using Gaussian filter. Second, the amount of transmittance change was taken for each image. Finally, the images were normalized from 0 to 255 pixels. Transmission decreases where granular gas is present. So decrease in transmittance change means gas field. The normalized image of the experiment 1 are shown in the video. The video shows the diffusion of volatilized granular gas at 50 times the normal speed, and it was possible to confirm that the gas concentration was thinnest about the gas source and gradually spread to the surrounding area over time. As the gas saturated, there was no change in the distribution of gas concentration over time. The normalized images of the experiment 2 are shown in the video. Spread and giving airflow at starting 5 minutes 30 seconds later, confirming that weak airflow caused the gas from the gas source to move to the left. Conclusion: the visualization of weak gas plume was successfully achieved. Future prospect, identification and visualization of multiple types of gases. Thank you for listening.
Right. We have time for 1 or 2 questions. Yes.
Can you tell me, curious, just on the frame rate of your visualization, and then on the nanoparticles, did you explore different sizes?
Nanoparticles sizes. This is same画像, same images. Silver nanoparticles is 3 nanometer, and gold nanoparticle is 3 nanometers. 3 nanometers. About 3 nanometers.
In your visualization, can you tell me what frame rate perchance? Your video recording, 日本語で話してください. Your video rate, can you tell me that?
Frame rate is 50 times faster. Frame rate 5 FPS.
違う. We'll talk after.
This is 1秒間には5回画像を撮って、これは50倍速している。Original is 5 FPS, but this video image is 5 times faster than original image. This video.
All right. Let's see. Yeah, maybe we move on to the next speaker. Let's give a big round of applause again. All right. Our 4th speaker is Tong, and he's going to be talking about some spintronic devices.
Okay. Hello, everyone. I'm Yujian Tang, and master first year student and from USL Lab, and our research is about the spintronic devices and My topic is strategies in suppressing the Skyrmyung Hall effect. Okay, and this is the table. And first, what is Skyrmyung? And topological risk protected spin tensor, and meaning is highly stable and difficult to destroy, and promising for the next generation memories and logic devices. And based on the spin rotations, and Skyrmyungs are mainly divided into two types. And then this is the Skyrmyung registrar memory. Okay, please wait. This is the Skyrmyung registrar memories, and advantage of this one, and high densities, high speed, and low power consumption. Okay, and when driving Skyrmyung's motions and its rotating spin structures experience a magnetized force and causing drift motions, and we call it Skyrmyung Hall effects, and which will cause the Skyrmyungs to reach the device edge and annihilate and risking the data loss. And our goal is to suppress the Skyrmyung Hall effect and enable stable Skyrmyung motion. Okay, and I will introduce some structures to achieve my goal. And the first method is to set the IMA boundaries at the edge of the racetrack. Yes, the IMA boundaries generates a repulsive force that can cancel out the magnetic force and allowing the Skyrmyungs to move in a straight line along the racetrack. Okay, look at the results: no boundaries and with boundaries. And in addition, the magnetic field of the repulsive force is also related to the width of the boundary. Okay, the second method is adjusting the radius of both DMIs and interfacial DMI. And DMI stabilize Skyrmyungs by promoting the zero spin structures and crucial for their formations and stability. And the both DMIs, both DMIs stabilize a broad Skyrmyungs, and while the interfacial DMIs favors nail-tight Skyrmyungs. By introducing the hybrid DMI Skyrmyungs with both broad and nails characteristics can be formed. From the results, as we adjust the hybrid DMI radius, the Skyrmyungs Hall angles decrease, and meaning that it's possible to eliminate the drift motion. Okay, the next method is to create a Skyrmyung. Skyrmyungs consists of a Skyrmyung core and surrounded by the opposite charge cells, and there results in a zero net topological charge, and which means the magnetic forces cancel out completely. And using such device to create a Skyrmyung by SOT. And for Skyrmyung, the two opposing forces cancel each other out and enabling straight line motion. Okay, the fourth method is to introduce electric field control, and this graph shows the schematic representations of the force contributions on the Skyrmyung dynamics. And in this method, by turning the applied voltage, we can suppress the Skyrmyung Hall effect at any current densities and also increase the transfer motion speed. Okay, the last method is anti-spheres magnetic coupled spin layer Skyrmyung. And in this approach, two Skyrmyungs exist in adjacent layers and are coupled anti-spheres magnetically. And because their magnetic forces are equals and opposite, they completely cancel each other out and eliminating the Skyrmyung Hall effect. And the figure C and figure E illustrate how the spin textures in the two layers mirror each other, ensuring balanced motions without Skyrmyung Hall effect. Okay, and the summary. Okay, I just showed 5 methods to deal with the drift motions, problems of Skyrmyungs. Okay, IMA boundaries, hybrid DMI Skyrmyungs, and electric field controls and anti-surveillance magnetically coupled spurious skyrmion. And there are also any other methods to eliminate the skyrmion Hall effect. And I will talk about my recent research. The skyrmion Hall effect is a new topic in our lab, and recently the research what I did is about the skyrmioniums, and I have reproduced the simulations for generation the skyrmionium, and I use this type of the device for generations, and this part shows the nucleations of the skyrmionium. Okay, and the right image displays the simulations of skyrmion and skyrmionium's motion, and confirms that the skyrmion Hall effect is indeed suppressed. Okay, look at the videos, and yeah. Okay, and I will fabricate the samples in the futures, and I think the difficult point is that the generations of skyrmionium, because it has narrower stability range than skyrmion. Okay, thank you.
All right, questions? Yes.
Thank you for a nice talk. Skyrmium, I'm not familiar with skyrmions, but it looks like that this defects, I don't understand how this is a stable defect. Is this a dynamic defect, or what stabilizes that defect, and how do you generate it?
The skyrmion Hall effect? Do you
No,
think
the skyrmium itself, of which type ever, how is this created, and what stabilizes this type of defect? I mean, this seems to be a high energy small defect that should dissolve.
I think it not need more too high energies, and I think it's stability based on its DMIs and PMA. For example, the PMA is perpendicular magnetic anisotrophies. Okay, and I think I don't know how to explain. The skyrmion looks like the spin. Yeah, the spin topologically protected spin texture is the.
Okay, thank you.
Oh, sorry.
All right. Yeah,
Thank you for the really nice talk. When you are creating the spin state with your tantalum for the writing the state, does the tantalum structure need to be nanoscale?
Yeah, the neo type skyrmion, I think it is easy to transfer, but for the broader type skyrmion, because it's spin rotations, since that means that it need more high energies to transfer and more stability, more stable.
And in your transport layer channel, is it sensitive to grain boundaries, or does it need to be single crystal?
Single crystal. Can you repeat the problems again?
Your racetrack.
Yeah, my racetrack.
Does it need to be a single crystal?
It's the multi-layers single. I can't get there's problem, sorry.
Yeah, no problem. Thank you.
Okay.
All right, we are on to our last talk. All right, our last speaker is Yuma Yamamoto. And okay, that's a long title. I'll let you explain it, okay? Thank you.
Hi, my name is Yuma Yamamoto from Kyushu University. Today, I will be presenting on the topic investigation of the effects of rectangular amplitude modulated discharge on high-frequency capacitively coupled plasma using PIC-MCC simulation. To begin, the rapid development and widespread adoption of AI and IoT have driven an increase in demand for semiconductor devices, including DRAM and NAND flash memory. In particular, technological trends in semiconductor devices are now focused on miniaturization and integration through the 3D stacking. As further miniaturization of 3D devices advances, the semiconductor manufacturing processes requires increasingly precise control of plasma processes such as reactive ion etching and plasma-enhanced chemical vapor deposition, which are fundamental to the semiconductor production processes. In plasma processes, parameters such as electron density and electron temperature exist as plasma parameters that determine the characteristics of the plasma. Here, we illustrate the significance of each plasma parameters in reactive ion etching and plasma CVD. As shown here, electron density, Ne, primarily determines the throughput, such as etching rate and deposition rate. And while electron temperature, TE, influences process quality, including selectivity and film quality. However, in low temperature plasmas for semiconductor manufacturing, Ne and TE generally exhibit a trade-off relationship, and independent control has not yet been achieved. Now, we introduce conventional plasma parameter control techniques in capacity-coupled plasma. First, there is a dual frequency capacitively coupled plasma, DFCCP techniques, in which multiple frequency components are applied to the electrode. This technology enables the independent control of ion flux and ion energy at the electrodes, which was previously difficult to achieve, but DFCCP faces fundamental impedance matching issues in experiments, making its implementation in mass production challenging. Next, in contrast to conventional continuous wave CW discharge with radio frequency voltage, amplitude modulated AM discharge, where the voltage amplitude is varied over time, allows plasma parameters such as ion incidence angle to change over time in response to voltage amplitude variations. This enables conformal thin film disposition on the sidewall of trench structures in TEOS PCVD. However, none of these discharge methods have yet achieved independent control of electron temperature and electron density. In our study, we achieved partial independent control of electron temperature using rectangular amplitude modulated discharge with PIC-MCC simulations. Now we will present our findings. In this study, we applied a rectangular AM waveform instead of sinusoidal type modulation to 10 millitole argon plasma and varied the modulation frequency from 1 kHz to 100 kHz. Here we show the time variation of electron density and electron temperature within one modulation cycle at each modulation frequency, as calculated by the PIC-MCC simulation. Specifically, the horizontal axis represents 1 millisecond for a modulation frequency of 1 kHz and 10 microseconds for 100 kHz.
At a relatively low modulation frequency of 1 kilohertz, the electron density exhibits temporal variations, whereas at 100 kilohertz, it no longer responds to the amplitude modulation. In contrast, the electron temperature significantly exceeds the CW discharge value during AM discharge. And this electron heating effect is observed even at 100 kilohertz. The increase in electron temperature at the rising edges of the rectangular amplitude discharge was also observed in PROES measurement using an ICCD camera, showing good agreement with the simulation results. These findings suggest that rectangular amplitude modulated discharge enables partially independent control of electron temperature. Finally, here is my conclusion with the 3D dimensional stacking of semiconductor devices. Higher precision control of plasma parameters, including electron density and electron temperature, is increasingly required. In our study, we demonstrated the potential for achieving partial independent control of electron temperature using rectangular AM discharge. These findings suggest that rectangular AM discharge can contribute to radical control in plasma processes, potentially improving selectivity in RIE and film quality in PCVD. That concludes my presentation. Thank you for your kind attention.
All right, questions? Okay, maybe I can start with one. So you emphasized electron temperature, right? What do you think would be the effects of having a wide distribution of electron temperatures?
What kind of distribution?
Like if you have different electron temperatures, would that affect film properties, morphology?
Yes, yes. And as I showed here, in RIE, the logical species determined by the electron energy through the dissociation processes, and also in PCVD, also radical species and radical density are determined by the electron energy which collide to the neutral species, neutral gas or neutral species. So this electron temperature increase make RIE and PCVD's quality of process good, making good.
Thank you. Right. If there are no further questions, let's give all our speakers a big round of applause. So that concludes the seminar. I believe there are more snacks if you want to grab something on your way out, but I strongly encourage you to spend some time with the visitors, talk to them, get to learn something about them, and they're very excited to be here as well. Thank you for your time.